Okay, so we're going to talk about Lesson 12.1, Introduction to Sequences. A sequence is an ordered set of numbers where each number in the sequence is a term of the sequence. And a sequence may be infinite sequence, which means it continues without end, which would be like the natural numbers, whole numbers like that. Or there are finite sequences which have a limited number of terms, such as the numbers 1, 2, 3, and 4. You can think of a sequence as a function with sequential natural numbers as a domain, and the terms of the sequence as a range. So values in the domain are called term numbers, and they're represented by n. Instead of function notation such as a parentheses n, sequence values are written by using subscripts. The first term in the sequence is a sub 1, second term a sub 2, and the nth term would be a sub n. Because the sequence is a function, each number n has only one term value associated with it. So here we have the terms 1, 2, 3, 4, and 5, where those represent n, and that would be the domain. And the term value then would be a sub n, which is 1, 1, 2, 3, and 5. These are actually called the Fibonacci sequence, and this sequence will be represented by what's called a recursive formula called a sub n equals a sub n minus 2 plus a sub n minus 1, where this a sub n minus 2 means the term 2 previously, and a sub n minus 1 always means the previous term. Once again, that's called a recursive formula. So first of all, we're going to do an example to where we use the recursive formula. And when we're talking here, it says they want us to find the first 5 terms of the sequence with a sub 1 equal to negative 2, and that means that's the first term of the sequence is negative 2. And a sub n, or to find the nth term of the sequence, or the next term, we're going to do 3 times a sub n minus 1, and the a sub n minus 1 here, that represents the previous number. I'm going to plug it in there. So this means I'm going to do 3 times the previous number, answer, and then add 2 to that. So here we have this situation that we're going to find these for. And so first of all, here we have 3 times a sub n minus 1 plus 2. So the first term was negative 2. So what I'm going to do is I'm going to put negative 2 in for a sub n minus 1. So I'm going to do 3 times negative 2, which would be negative 6, and add 2 to that would give me negative 4. Now to find the next term then, we're going to take that answer, negative 4, and put it in for a sub n minus 1. So we're replacing that, and so then we multiply that and add 2, so we get negative 12 plus 2 would be negative 10. Then we take that answer and plug it in. So it would be 3 times negative 10 plus 2 would be negative 28. And then 3 times negative 28 plus 2. So that would be negative 84 plus 2 would be negative 82. All right, so when it says a sub n minus 1, that means we're going to use the previous term answer to get the new answer. So if we were looking at, let's do this, check it out here, 1a. So it says the first term is negative 5, and to find the next term, we're going to do a sub n equals a sub n minus 1 minus 8, which means that the a sub n minus 1, we're just going to replace that with the previous answer. So to find the second term, I will do negative 5, which was my previous answer, and subtract 8 and get negative 13. And we'll take negative 13, put that in for a sub n minus 1, subtract 8, get negative 21, and so on. So that's using the recursive form. Okay, so the next example is going to involve using what's called the explicit formula. And an explicit formula defines the nth term of the sequence as a function of n, which basically to you, this would mean that we're going to do something like the y equals in the terms of x. So here we have this problem here. A sub n equals 3 raised to the power of n minus 1. And you could think of this as the same as y equals 3 raised to the power of x minus 1. So when we're talking about using the explicit formula, we're basically talking about using like a y equals. So that means then all I do is take the values of n, the term number, and put it in for n to find the answer. So in this case, to find the first term, we put 1 in for n, so we have 3 to the first minus 3, which would be 2. Then we'll do 3 to the second power, and 3 squared is 9, minus 1 is 8. So then to find the third term in the sequence, we just put 3 in for n. So we have 3 to the third. So 27 minus 1 is 26. Then put 4 in for n. So we get 3 to the fourth, which is 81 minus 1 is 80. And then put 5 in for n. So we get 3 to the fifth minus 1, which is 243, minus 1, which is 242. So if it's an explicit formula, then we just put the value of the term number in for n. So like number 2a here, we'll put 1 in for n, so which means we'll have 1 squared minus 2 times 1. So 1 minus 2 is negative 1. And then 2 squared minus 2 times 2. So 2 squared is 4, minus 4 is 0, and so on. So explicit formula, we're going to replace a sub n minus 1 with the last term. And for recursive formula, we replace a sub n minus 1 with the last term. And for explicit formula, we will replace n with the term number. Okay, so the next thing we're going to do is we're going to look at writing rules for sequences. So a reminder that our patterns, so if we have a linear pattern, have constant first differences. Quadratic patterns have constant second differences. And exponential patterns have constant ratios. So most of the explicit rules we're going to end up writing are going to be one of those three, and then sometimes you just have to compare them to the numbers compared to the value of n to help figure them out. So here we have this sequence, 5, 10, 20, 40, and 80. And we're going to look at the possible different rules. And, you need to look at the numbers, and maybe you can figure out what it is right off the bat to be able to help you. But we're going to go ahead and look at the differences in this case, first of all. The first differences, so we subtract. 10 minus 5 is 5. 20 minus 10 is 10. And 40 minus 20 is 20. And then 80 minus 40 is 20. There's 40, excuse me. So this is definitely not the first difference. If we calculate the second difference with these numbers, 10 minus 5 is 5. That's 40 here. And 20 minus 10 is 10. So it's definitely not second difference either. So I'm going to check the ratios then. So if we do ratios, if we do 10 divided by 5, we get 2. If we do 20 divided by 10, we get 2. 40 divided by 20 is also 2. So this is a constant ratio, which means it's exponential. So I should have something that looks like the form y equals a times b raised to the power of x, where a is our starting value, b is our constant ratio, and we have our exponent. We're going to do that with the common ratios here. So one of the things we can look at is comparing it with term number also. So let's write our term numbers. So here's our term numbers, n. So we have 1, 2, 3, 4, and 5. And here's our a sub n. would be 5, 10, 20, 40, and 80. So this would be 5 times 2 to the power of 0, because 5 is our number and we multiply our constant ratio. This would be 5 times 2 to the first power to get 10. This would be 5 times 2 to the second power, and 5 times 2 to the third power, and 5 times 2 to the fourth power, because we have to get 10, we have 5 times 2, 20 is 5 times 4, 45 times 8, and 80 is 5 times 16. So we want to compare the values of n to the exponents in this case, and if you notice, you can see that the exponent is always 1 less than the power of n. So when we write our recursive formula, then we will say a sub n equals 5, which is our starting number in this case, times 2, and the exponent, since it's 1 less than the term number, I'm going to say the term number n minus 1. So this would be 5 times 2 raised to the power of n minus 1. Okay. And let's look at another example here. Here we're going to look at our differences first of all. So we're going to subtract. 4 minus 1.5 is 2.5. 6.5 minus 4 is 2.5. 9 minus 6.5 is 2.5. And that follows here with 11 minus 9 is 2.5. Okay. So once again, we're going to list our term number. So we've got n here, which is 1, 2, 3, 4, and 5. And here we have our a sub n. So 1.5, 4, 6.5, 9, and 11.5. And so we want to look at what we have to do to be able to get there. So since our constant difference here is 2.5, then we have to look at adding. So if I take 1.5 here, and I add 2.5 times 0, we will get 1.5. To get 4, we have 1.5 plus 2 times, or 2.5. 2.5 times 1, and this would be 1.5 plus 2.5 times 2, 1.5 plus, we add 2.5 3 times, and this would be plus 2.5 4 times. So if we have our nth term, then our rule would be a sub n equals 1.5 plus 2.5 times, and you notice once again our values over here in the parentheses are 1 less than the term number, so this would be n minus 1. And so you don't want to leave it like that. We want to simplify this expression, so we would distribute the 2.5. So we would have a sub n equals 1.5 minus 2.5 is negative 1 plus 2.5 n. And that would be our rule for the sequence, our explicit rule. Now I want to take one more look at one more. I want to take a look at 3b here. And a table really helps you. So if we list our values of n, 1, 2, 3, 4, and 5, and our term 1, 1/2, 1/3, 1/4, and 1/5. That you can see in this case that we just want to see there is no explicit or there's no constant ratios or constant differences here. You just kind of have to look at it and figure it out. And if you notice in this case that our numbers here, that here the term number is in the denominator, so that term number is just the value of n, so this would just be 1 over n, and that would be our explicit rule. Okay, our next example is using a physics application. Here a ball is dropped and bounces to a height of 4 feet. The ball rebounds to 70% of its previous height after each bounce. Graph the sequence and describe its pattern. How high does the ball bounce on the 10th bounce? So if we look at this, we have our value of n, which is going to be the bounce number, and a sub n would be the height. So it says the ball is dropped and bounces to a height of 4 feet. So on our first bounce, it's going to be at 4 feet. On our second bounce, then, it's going to be 70% of that. So 4 times 0.7 would be 0.28. So we did 4 times 0.7. And then to get to the next one, we would take 0.28 and multiply that by 0.7. So let's see, so that would be 1.96. And that would be, oops, this should be 2.8, not 0.28. And then we have 1.96, and that would be 4 times 0.7. And how many times did we multiply 0.7 that time? Then we multiplied it by 4.7 squared. So our rule here is going to be that a sub n would equal 4 times 0.7 raised to the power of n minus 1. So to find the 10th term, so I could write that as a sub 10, I would do 4 times 0.7 raised to the power of 10 minus 1. So if I pull out my calculator, let's see, here we go. If you find the 10th term, we will do 4 times 0.7 raised to the power of 9, 10 minus 1. That will give us 0.16 feet. So we get a sub 10 is equal to 0.16 feet. So on the 6th bounce, it would bounce to that height. So I would start it out now in my graph. I would have, oops, that's not the first bounce. We'd have the first bounce is at 4, and 2.8, and 1.96, and so on. And the graph is going to curve going down. Okay. All right. And so that's using our physics application or an application of sequences. Okay, we have one last example here, which is using something called an iteration. And when we talk about an iteration, we're talking about following a pattern. And here's the example in the book that you can see that we start here in this with a single triangle. And then they cut a triangle out of the middle, so we've taken from one whole triangle now that we have 3 triangles. So then we take and we cut the hole out of the middle of each of those triangles. So we take each of this triangle here, and this one here, and this one here, and we made each of those into 3. So, well, here I'm going to have, so I have had 1 triangle, and then 3, and then we have 9. So what happens each time is we're multiplying by 3, which means that we have an exponential. So that would be using the function, in this case then, a sub n equals 1 times 3 raised to the power of n minus 1. And to be able to find that. But you have to look for the pattern. What is it doing? So in this case, they multiply. Instead of having 1, we have 3, then 9. So if you examine this closely enough, you can see that they're multiplying by 3 each time. So let's look at this example we have here. It says find the number of triangles in the 7th and 8th iterations of the Sierpinski triangle. So we're looking at here, by removing the center of each triangle, each iteration turns every triangle into 3 smaller triangles. So the number of triangles triples with each iteration. So we've got 3 raised to the power of n minus 1. So to find a sub 7, the 7th term, we're going to do 3 raised to the power of 7 minus 1. And then to find the 8th term, we'll do 3 raised to the power of 8 minus 1. So this would be 3 raised to the power of 6. and 3 raised to the power of 7 to find those values. So we have 729 and 2,981. Oops. Missed it here. And this one was, let's see, once again, 2,187. And that would be the example of iteration. So let's go ahead and look at check it out in this case also. And if you look at the iteration here, it says find the segments in the next 2 iterations. If we look at the first one, here we have 1 segment. And then that 1 segment has become 2 segments when I cut the middle out. And when we cut the middle out here, then that 2 becomes 4. So then if I cut the middle on the rest of these, then if I cut the middle here, oh, that's too thick, we don't want that. So if I cut the middle out here, 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 and here, now I've divided that and I have 2, 4, 6, 8 on my next one. And then if you see the pattern, we multiplied by 2 each time, and so the one after that would be 16 segments. And that's the end of lesson 12.1, using sequences.